start recording. Okay, so we're back. All right, so a few things. This is the first semester I tried to use Turnitin, and evidently one of the things that I did was that I made it so that Turnitin, the date was impossible for you to actually turn in the assignment once you were done with it. Okay, so I think I fixed that. And so try to turn it in. If it still doesn't work, then we'll just bag it and have you email things. But I'm gonna try it out. Give it one more try. Now, this lab that you were already assigned isn't due until 2 weeks from last Wednesday, so a week from today. And I made that announcement 2 weeks ago, but I realized I might have talked too fast or something. So you still have another week for the lab that was assigned. Officially, what I kind of did was combine 2 lectures into the first period, and then you were supposed to work on the lab during that second week when I wasn't here. So I kind of counted that as the beginning of the lab. So you had 2 weeks after that. So next week, that first lab will be due. The lab that I assigned today it will be due 2 weeks from today. All right. Okay. So and last week's lab was basically just walking you through the software. And today's lab, we'll introduce it when we get to it, is on coordinate systems. All right. That should cover any. I had a few questions on that from emails and stuff, but if there are any other questions on labs and turning them in, let me know. So if we go to course materials and week 2, I'm going to get the lectures. So the lectures are broken into 2 pieces, although this is just one week in your book. So this is a little less material to go over in one time period. Now, if I know I have some familiar faces in this course from last semester, and I said this last semester, but in order to do both cartography and GIS, you need to understand information about coordinate systems, and both of the courses aren't required for everybody. So some of this may seem like a little bit of a repeat for those of you who have taken GIS. I made, actually, this time I decided to use Dr. Carr's slides, so the slides will be different, so maybe you'll learn something new. So we've got 2 lectures here. We'll start with coordinate systems, and then we'll go on to the other one. Yes, go ahead. Okay. Every time we teach the class, I do have just before the test, we have a discussion on what the tests are like. But the tests are usually a mix of some multiple choice and some short answer. And the tests are mostly covering the lecture material. Most of the lecture material is like expanded in the book. Fortunately, the book doesn't cost very much, so I would suggest getting it. It's not super expensive. The tests are graded. So I grade all the tests. Usually they're like out of 50 or 100 points, depending on how long the test is. And I do often make so if the average grade is lower than like somewhere between 78 and 80, I usually adjust it so that the average grade is between 78 and if the average grade is higher than 80, I don't bring it down. But anyway, I go over the week before. We kind of do a review, and I have the test made at that point, so I try to make sure everybody's aware of what's on the test. Is that a good answer to the questions? All right. Okay, so Dr. Carr's slides are in PDF format, so it looks like we can still get through them. See if that advances. It does. All right. This is very similar to the content in the cartography course. But before we get into it, I want to do a little bit of a review. Okay? So last week we talked about, I want to take this off first. A little bit of review. We talked last week about, or not last time we met, about geographic data. And we talked about like trends and what a GIS is and all of that stuff. And that stuff's important, and you should read and learn about it. But one of the big things, or probably the biggest thing, that I wanted you to get from last week is what is geographic data. And geographic data is information about the world stored in a computer. And there are a few different ways to store that data in a computer, but we categorize them in two ways. But both ways have a method for storing the coordinate system of the things that we're trying to model out in the real world. In other words, the coordinates and the attributes. So they store both of that information. Where is it, and what is it that we're storing about that information? Okay? In this class, we'll probably focus a little bit more on, well, at least for the beginning part, a little bit more on what we call vector data. In other words, we take everything in the world, or everything that we want to model in the world, not everything, the things that we want to model in the world, and we think about them as either points, lines, or polygons. So this building could be a polygon. Or if we zoom out really far, we could think of it as a point. Okay? And then the attributes are the other information, the what about that building that we want to store. All right. And then we also talked a little bit about the raster data model. But in either case, we know, with the raster data model, we know the XY location of the center of every cell, or we know the XY location of those points that either are points, or they make up a line, or they make up a polygon. Okay? So today, we want to talk about more about what coordinates are, since we'll need to store those coordinates in the computer. We need to find out what is a coordinate. And that may seem like a really basic question, perhaps. Perhaps you're like, I know what a coordinate is. It's latitude and longitude. Okay, well, maybe you know that. But we're going to talk about some issues with coordinates, and also we're going to go a little bit further than just latitude and longitude, although we are going to talk about that. So to start off, we're going to talk about coordinates and datums, and talk about measurements of the Earth. This is something that I did bring up in my cartography class, but it's important. One of the first measurements of the Earth was taken by a Greek librarian, geographer. In other words, he studied a lot of different fields, and he was determined to determine the circumference of the Earth. And the way he did that was actually looking at the difference between where the sun fell or caused a shadow in two different locations that were a known distance apart. Okay? And so he could use angles. We're not going to recreate that or anything, but for those of you who've taken a college algebra course, you know that with trigonometry and angles, we could figure that out. So he estimated that the Earth could be about 42,000 kilometers. In fact, neither kilometers or miles were units of measure in his day. So he used some other unit of measurement. But he measured that, and he was pretty close, which is kind of exciting for that period of time. But one of the things that he proved, or that he was pretty sure of, was that the Earth was round. Okay, and that information would get lost by Europeans and then rediscovered later. But this phenomenon that the Earth is round, or this fact that the Earth is round, does present a problem to us as GI scientists or geographic information scientists. When we want to store information as coordinates inside XY locations, inside of a geographic information system, we're dealing with a round Earth. Now, let's say our study area is just a very small portion of the Earth. Okay? Well, the smaller portion of the Earth that our study area is, the closer it actually is to being flat, okay, because of the huge surface that we're on. The main problem that we have is that calculating things like distance is a problem on a circular map. I mean, you can calculate the distance, okay, but it involves more complex math than we usually use on a day-to-day basis. Everybody knows how to calculate the distance in a Cartesian coordinate system, right? I mean, what's the formula that we all use to find the distance between 2 points in a Cartesian coordinate system? Anybody answer that? Like in geometry, if I ask you, Pythagorean theorem, yeah. So a squared plus b squared equals c squared. C squared is the distance between the 2 points, and we basically use a triangle to find that distance, right? Well, this distance, if we think about it on a globe, isn't that simple. We can't take the latitude and longitude of this point and the latitude and longitude of this point and plug it into the Pythagorean theorem. And also, angles get a little funny on a globe, and sometimes, in fact, a lot of the times, the compass direction to a particular location isn't actually the fastest way there, or the one that will take the shortest distance there. Okay? You know, it's like, who's ever been on a transcontinental flight? Maybe not everybody, probably not everybody, but if you've gone from Europe to the United States or back, I only done it once or twice in my life, or twice, I guess. If you fly that direction, if you fly that route, you'll notice you get pretty far up north. And the reason for that is that it's a shorter distance going that way. But it's not always the same. If you were to think about the angle, the direction that you're flying, you're actually constantly adjusting your angle to stay on the shortest distance path. So converting from modeling the world as flat to the actual world being round and going back and forth presents a few problems. And as I said, these problems get less and less the smaller your study area is. However, oftentimes the smaller your study area is, the more precise you want to be. The more tied down to the actual coordinate you want to be. So it's more important that you account for these things. So you still have to account for them no matter what scale you're at. All right, so we're going to talk a little bit about coordinate systems, and the first coordinate system that we're going to talk about is latitude and longitude. So where you are. Okay? So latitude and longitude is just the angle from the center of the Earth. Okay? The angles are a little bit different actually going north to south than they are east to west. Going north to south, we just start at 0 and we go up to 90, meaning straight up at the equator. So if you're at 45 latitude, then you're halfway along that angle from the center of the Earth up to the North Pole. All of the latitude lines are parallel to each other, and in fact, sometimes they get referred to as parallel. Okay, the lines of longitude, I like to think of them like sectors of an orange, because I like to eat oranges. So we've got like little orange sectors. We go around the Earth, we get different longitude lines, and technically they go from 0 to 360, but typically the way that we organize it is to go from positive 0 to positive 180, or going around the other world, way around the world, 0 to negative 180. All right, okay. Also, one of the things is the world actually isn't exactly round. And I'm not even talking about little undulations. I mean, we all know that we've got Mount Everest, right? We've got mountains in our own country. So even if we account for the fact that there are some mountains in the world, it's still not exactly round. In fact, it's a little bit wider than it is tall. Okay, so it's a little bit wider. So scientists believe that's due to the Earth spinning. It's wider out than it is tall, and so oftentimes we'll model the Earth as what we call an ellipsoid. So we say it has an ellipsoidal shape. An ellipsoid is a mathematical model of the Earth. And what we often want to do is create a flat map, especially as geographic information scientists. And the reason that we need to create a flat map is to measure things like areas and distances and angles. However, that's not always possible to measure angles and distances. It's not always possible to measure angles and distances in the same map. Some maps are better at measuring distances. Some maps are better at measuring angles. Some maps are better at measuring areas. So we need to think about what coordinate system we want to use in order to do that. Okay, now I already said the Earth isn't completely round, right? It's more like an ellipsoid. And this is actually what we model a lot of the times. We model the Earth as an ellipsoid. However, you should know that for like really exact measurements of sea level and things, we would use a geoid. Okay, the geoid is not mathematically described, and it does change over time slowly. Okay, it's the point at which the gravity field equals mean sea level. In other words, if I were to take a measurement of how much gravity there was, and as I go up and down in elevation, whatever that point is of mean sea level, that's the zero line for the geoid. So the geoid kind of like goes up and down throughout the world. And typically when we're making maps, we don't use that surface. We use the ellipsoid, which is a mathematical approximation of the Earth. That's what we typically use when we're making maps. So every coordinate system needs an ellipsoid. A spheroid is an ellipsoid that that assumes the world is a sphere. Okay? And there are maps in common use actually that use a spheroid. For example, the one that's widely adopted by Google. If you go onto Google Maps, okay, that web Mercator uses a sphere because they're not necessarily concerned about accuracy in terms of distances, or they can use a different set of data to measure those distances that they want to return to the user. Okay, so this is a more fancy way of saying that typically map projections and coordinate systems are developed from a single set of equations. They're mathematically simple. In other words, the spheroid really only has two parameters that define it. So imagine I have a circle. How do you define a sphere? Well, really you only need to know the center and how long the radius is, and you define a sphere, right? Okay. Well, defining an ellipsoid only takes two numbers. One, it's called the semi-major axis. Instead of the radius, the semi-major axis is the longer axis that goes out to what we call the equator, the center this way. The semi-minor axis, the shorter of the two axes, goes from the center up to the pole. So once you define the semi-major and the semi-minor axes, you've defined an ellipsoid, and that's usually the way that ellipsoids and map projections are defined. Okay, geoids are defined by local transformations much more computationally demanding. Another way to say this, probably a better way to say this than I would say it, is that geoids are empirically defined. In other words, they're found out with instruments. You go out and you take an instrument and then you take a bunch of measurements and you kind of interpolate in between the reference measurements that you collected. Okay? Whereas a spheroid is defined, you specify the center of the Earth, and it's mathematically simple. Okay. So oftentimes, if you, sorry, you had a question?
So would geoids be more accurate?
I don't know if accurate's the right word, but they're definitely a truer approximation of the Earth. Or, yeah. And what I was just about to say is that you'll notice that if you get height above ellipsoid measurements, because typically in GIS, if you get a measurement and you say, okay, well, the elevation here is 57, okay, 57, one of those meters or feet or whatever, and you would need to know if that was an ellipsoid height or if that was mean sea level from the geoid. And typically, you will see areas where you're like standing right on the ocean. Not typically, but if you were using ellipsoid heights, you could be standing right on the ocean and receive a value 50, between 25 and 50 feet, because the ellipsoid does not approximate the Earth that well. It's just an approximation. But it's mathematically simple. It's fitted to the Earth. So in some places, it's really far off. In some places, it's very close. But on average, by definition, on average, the error is supposed to be zero, because there's some highs and some lows, and then averages out. Okay. Now, some ellipsoids are designed so that they only fit a certain portion of the Earth. They're designed for like North America. Some of them are designed for the whole world. Okay? So there's the one that is most often reported by your GPS was established in 1984, so it's called WGS 84, the World Geodetic Survey of 1984. Okay? The one for North America, that's actually very closely related to it, to WGS 84, is called NAD 83, North American Datum of 1983. Okay, so here's an example. This ellipsoid is designed to fit the entire Earth. Okay? This ellipsoid is designed to fit a specific region. I don't know which specific region, maybe like right here. It fits the Earth area very well, but it has a problem right there. A problem right there. Okay. So the origin is the center of the Earth. And sometimes the center of the Earth is actually modeled in a different location, okay? Particularly in region-fitted ellipsoids. Notice that the center of the Earth is off a bit from the center of the Earth. Typically, we refer to that tie point back to the Earth as the datum. So datums and ellipsoids are both requirements for building a map projection, which we're building up towards. Okay, so here's the North American datum of 1927, NAD 27. That's a very common datum for North America. So a lot of older data will be in this projection. Will be in this datum using that ellipsoid. And here is a slide, a little bit hard to read, that compares the 1983 to 1987. Usually, when you bring up two data in two sets of data, two data layers into ArcGIS that are in different datums, they'll only be slightly off. You'll say, okay, that's a datum shift. You see them and they're slightly off. It's usually a difference in some of the projection parameters, most often the datum. Okay? If they're really far off, particularly if they're like factors of 3 off, then it's probably a units issue. So one projection is in feet and another is in meters, and then they'd be off by almost 3 exactly, right? But the datums are usually just off by hundreds of feet rather than being off by everything multiplied by 10. So this is not something like you've memorized for a test or anything. This is just information to drive this point across, that these are the things that make up the differences. That the datums in different datums that were created, that create different ellipsoids, that are used to create different ellipsoids, have different semi-major axes and semi-minor axes. See how they're different? But they aren't different by that much. This one's off by 200 meters, and that one's off by less than 100 meters, actually. Okay? WGS84 and NAD83 are almost identical, okay, to each other. There's a very small difference in between these two data sets. And as I mentioned before, GPS systems by default are using WGS84. In fact, that's what they're actually using. If they're reporting something else, it's because you've told it to report something else, and it's doing the math to change that. Right? Now, yeah.
So a datum is the vested ellipsoid that passes around the Earth from a certain point?
Yeah, so a datum is the center of the Earth along with the other information, the semi-minor and the semi-minor axes. The ellipsoid is technically just the semi-minor and semi-major axes. So the datum is the semi-minor and semi-major axes along with the tie point to the center of the Earth.
Okay, so it's based off, each datum is based off a particular spot on the surface of the Earth.
No, each datum describes the Earth in a different way. And it will turn out to affect the coordinate location of where things are by just a little bit. So a datum and an ellipsoid are almost interchangeable words. Okay? The datum is all the information needed, the description of the semi-major and the semi-minor axes, and the center of the Earth. The ellipsoid is just technically the semi-major, the two axes that define the center of the Earth. I mean, that define the shape of the Earth.
But it doesn't include the center of the Earth?
Right. I mean, technically, an ellipsoid doesn't include that. But they'll often use those terms interchangeably. So if you were to define a datum, it would actually have you define the ellipsoid and define the tie point to the center of the Earth. If you were to define, there's really no reason to just define an ellipsoid. You need a datum to establish the center, what the center of the Earth is and how big the Earth is. And really, that will define where things are in space. So if you can see, if the Earth is shaped slightly differently, then the angle from that is in a slightly different position. And so what is, like, let's say, we're at like 80-something degrees west and 20-something degrees north, okay? I don't even know if that's exactly right, but it seems to be in my head. Maybe 30-something. But that location, those two angles would be in a slightly different place if that Earth was shaped slightly differently. And that's the measurement that we're talking about. So all coordinate systems, we haven't even started talking about map projections yet. All coordinate systems need this information, the datum. When we talk about projected coordinate systems, in a few minutes, they need some additional information, but they all coordinate systems start with a measurement of the center of the Earth and the shape of the Earth. And one of the things that we'll talk about later is that typically we use a standard projection so that other people can get back to the same coordinate or use the same coordinate we have. And so you don't actually define your own datums. You just use datums that already exist. You don't do that too. I mean, maybe like some point in your career you could work for the U.S. The NGS, the National Geodetic Survey, establish datums, but for the most part, we just use these things as geographers or geologists or people that are measuring the Earth. An older datum is actually Clark 1866. There's WGS 84 showing how far off it would be. Obviously, these are exaggerated. The Earth looks nothing like that yellow blob, right? Okay. Some other NAD, North American datum of 1983, and the International something reference frame. I forgot exactly what it stands for. So, really, when we talked about latitude and longitude, the whole reason that we talked about datums was so that you understand that a XY location, or not an XY location, a latitude and longitude location is not always as simple as that. If I want to bring up multiple layers in my GIS system and analyze them together, it matters if the datum that I use is the same as the datum that somebody else used if I want to combine the data in my GIS system. So if I want to analyze things, like if I wanted to determine where are the new roads, right? And I brought up roads from, your book actually has a picture of this, but roads from NAD 27 and roads from NAD 83, the roads would be slightly off. I'll just Google this. So if I have an example, I'm sure somebody will show this. Nope. Not getting. Oh yeah, here we go. All right. So here's some data, some road data that's been drawn. I don't know. Let's just say the road data was drawn in NAD 83, and then the image was referenced using NAD 27 or vice versa. Then they would be off. So you see how this road is off from that road. They'd be off a bit. And so as a GI scientist, geographic information scientist, you should be able to recognize this and try to rectify that problem. And that's why we were going over datums. Datums are, they'll create small differences in where things are, even using latitude and longitude. We talk about what these mean: latitude, degrees from the center; longitude, degrees from the center, but going around in a circle rather than up and down. Right? So, north of the equator, positive values. So that's, I think we're at, like I said, between 20 and 30, 20 and 35 or something. South of the equator, like if you went down to South America, all the latitude values would be negative. Likewise, in the something that we often forget, we're here in the Western Hemisphere. Usually, we talk about our longitude values as negative. So if I said we're negative 83 degrees west, that means that we're 80 degrees from the center of the Earth over from the prime meridian, which is in England, outside of London. Okay. And lots of times we learned about latitude and longitude lots of times, like in high school. But it's just good review. Actually, did go there on the trip to Europe. There, there's the prime meridian. You can go stand in the eastern Western Hemisphere, the Royal Observatory in Greenwich, just east of London there. Okay? All right. Now there are a few different ways, even in the GIS system, you'll bring up data and you'll want to find out what the latitude and longitude is. There are a few different ways to express degrees. Okay? One of the ways that you probably learned about is degrees, minutes, and seconds. Degrees, minutes, and seconds. So a degree is just 360th of the way around, right? So that's pretty easy. What's a minute? What's that? It's 60 seconds. That's true. And it is 60 of these seconds. So a second is 60. So 60 seconds is 1 minute, and there's actually 60 minutes in 1 degree. So just like there's 60 minutes in an hour, it's like hours, minutes, and seconds. These are degrees, minutes, and seconds. So there's 360 degrees of longitude and 360 degrees of latitude. But then there's 60 minutes in each degree and 60 seconds in each minute. And so you can describe a more precise location if you specify degrees, minutes, and seconds. So remember, what was the circumference of the Earth? It was 24,000 something, right? I forgot exactly what it was. What's that? 249 what? Like that? No, 902. Okay. So that's the circumference of the Earth in what, miles, right? Yep. Okay. So if we divide that by 360, so each, if we were standing at the equator, each degree is 69 miles. So if I were to report my degree, my latitude and longitude in degrees, you'd only be able to find me like in a 69-mile radius. Okay, that wouldn't be acceptable if I was like a drift. You were trying to find me 69 miles. That wouldn't be very good. Now, if I divide that up by 60, now I'm down to a 1 mile radius, or a little bit over 1 mile, right? And a second, if I divide that up, divide that by 60, now we're down to 2/10 of a mile. Okay, so we're getting pretty close. 2/10 of a mile would be like from here to one of the other buildings I could see. It's pretty close, right? However, you might want to get more precise than that. Well, the way to get more precise than that is to just use decimal seconds. So this is 39 degrees, 18 minutes, 56.88 seconds. And at that point, we're getting down to like feet. Really, really small point. We're in really small areas. Now, the thing about latitude and longitude is I've converted it to feet, I converted it to real linear units. But as I go further north, 1 degree, picture I'm standing on the North Pole and I take 1 step off the North Pole. Now, if I can go all the way around the Earth, maybe in 7 or 8 feet. So if I divide the degrees up by 360, now we're getting really precise. We're getting really small. So here's the location of Hattiesburg. Here's the location of Long Beach. When expressed as degrees, minutes, and seconds, with some decimal seconds, is the way you usually say that. Okay, now, GIS systems usually deal better with real whole numbers, okay? And sometimes you'll see degrees expressed as decimal degrees. Decimal degrees are simply put just the number of degrees and then point whatever. So this is still an angle. 31.3158 degrees north. And since it's negative, it's 89.3086 degrees west from Greenwich. Right? So that's I was wrong about being 20. It's 30. Of course, Long Beach is getting close. Right at a little bit above 30. So decimal degrees and degrees, minutes, and seconds. Now, we can convert back and forth between these, right? It's pretty easy. So going this way, we take 31 degrees, that's fine. 18 minutes is 60th of a degree. So we take 0.6, multiply by 18, and just go out that way. Okay? But oftentimes, the computer software does it. It's good at that. It's good at converting back and forth between those two ways to say it. All right, so you can express things in both ways. So here's the formula. If you wanted to convert back and forth between decimal degrees and degrees, minutes, and seconds. You do it in Excel. Right? And I kind of already did an exercise like this, but we're talking about 1 degree of latitude. I use miles, but we could use meters. And we're getting more precise as we get further out. When you are using degrees and you want a very precise position, even if you go out to, what is that, tens, hundreds, thousands, 10,000s, 100,000s. So 100,000ths of a degree is still over a meter. So if you're trying to get a really precise location, like you want to establish the edge of a parking lot in this location, you still probably want to go out a few more decimal places if you're dealing with degrees. And these, of course, change depending on how far north you are versus south you are. Oh, one thing to ask. So does the length of a degree change? Which one is it almost constant for? Latitude or longitude? Yes, it is. It's almost constant for latitude. You can see that because these are parallel, but because of the shape of the Earth is not, we usually model it as an ellipsoid. Because it's not perfectly round, it does change a bit. It's not exactly the same, but it's close. It's way different than the for the length of longitude. That changes a lot. Between two longitude locations. That goes all the way from basically 0 at the North Pole out to what we figured out 69 miles or whatever. Okay, that's the end of the first set of slides. And I think we're right on track. Okay, we usually get out of here to 2:40, and then we'll do the lab after that. All right, so map projections and latitude and longitude build on the next concept. It's not like there's two different types of coordinates. Well, I mean, kind of like there are two different types of coordinates. But when we model the Earth and use Cartesian coordinates to locate locations, I'm going to try to open this up and it only opens up now. When we try to model the Earth and come up with Cartesian coordinates, we're building off of latitude and longitude coordinates. So all these map projections are based on a datum still, which is based on an ellipsoid and a model of where the center of the Earth is. Okay. So when we use latitude and longitude, we call that a geographic coordinate system, or sometimes we call it a spherical coordinate system. That's latitude and longitude. Now, when we talked about this in cartography, we said you really never want to make a map in that thing. But when we're doing GIS, sometimes it's fine as long as we're not trying to calculate areas or distances. It's okay. Map projection. Map projection, sometimes we call that a projected coordinate system. It's a mathematical model to portray the curved surface of the Earth on a flat surface. So now we've got a second model. Geographic coordinate systems require a simple mathematical model for the shape of the Earth and the center point. We're going to build that out once further. We're going to use a mathematical model to turn the round Earth and smash it into a flat surface. So, you know, if you take, I'm using an orange too much today, right? I like oranges. But if you take apart an orange, you could try to make it flat. That's the second step, a mathematical model to take the round earth and make it flat. And it's easier to do, this is the part where it's easier to do this if we're just talking about a small portion of the earth. But there are ways to, and it's a little easier to think about for doing the whole earth. So we'll talk about that. So in order to specify a map projection, we do need to specify a regular coordinate system. And the coordinate system is based on a reference ellipsoid / data. You can use those words almost interchangeably. Okay? And then we take that round surface and we make a map projection. Here's two different map projections that might be used for different purposes. This is a very famous map projection called the Mercator projection. Okay? The Mercator projection has been around for a really long time because what's great about it is that all lines represent true compass directions to that location. So if I want to sail from England to the United States, I can measure this angle on the map, the true angle, just like using that as 0, and this would be the distance off 0. I can measure that, and I could set my compass. I don't know if this is how people drive big boats, but I could like be with my big steering wheel, what do they call it on a boat? Anyway, but if I kept looking at that and steering in the right direction with that angle, I would get to North America. Travel. I may not have taken the fastest route, in other words, the least distance, but I could go exactly along that path. And that's what this map projection was actually created for, but it is used a lot today. It's very common. In fact, this is what Google has adopted as the standard. Like if I pull up, I'll do this, maps.google.com, and you zoom out all the way, you'll notice that projection is the same. All the way. I guess it won't let me zoom out all the way. Probably because it doesn't want, well, here, I'll just zoom up. See how large Greenland looks and how large Antarctica look? Well, that's because of the way this map projection works. I remember I had one of these on my wall as a kid, and I was like, I gotta get to Antarctica someday. That place is huge. But it's not that big. All right. So I'm in Antarctica. So this map, in contrast, is the equal area map, and it looks distorted in a different way. It's distorted so that the areas are all correct, but it distorts the shape of the objects pretty badly. This one actually. One of the things that, if you think about it in your mind, this should make sense, right? If the shapes are pretty close to the same, then the angles are pretty close to the same. So this one actually doesn't distort shapes very much, and this one does. But this one allows for angles. This one allows for area calculations to be more correct. In reality, like Mexico and Greenland are about the same size, although Greenland is horribly misshapen because of the distance. Okay, so we already showed this slide like that. So these are the different trade-offs that we'll make when we take the Earth and try to make it flat. These are the different trade-offs. We've got the shape, or sometimes we call it the conformality. And the reason why I bring that word up here is not to sound fancy, but oftentimes the name of the projection will have the word conformal in it. And so you'll see that word conformal, and you'll know that what they try to do is preserve the shape of an object. A really popular map projection for North America is called the Lambert conformal conic. And so you can tell that they are trying to optimize shape in there. Area is another thing that some maps try to preserve shape as to the detriment of these other things. So in all of these things, you get to like, you know, pick one, and then sometimes you could pick two, and it's a balance. It's referred to as a balance projection. Okay? Area, distance, and direction. So distance is just, I'm going to measure from one location to the next, and direction preserves the direction or angle from a point to any other point. Area, distance, direction, or shape. So you can memorize it however you want. Here we have it set up as SAD, S-A-D-D, or it could be ADS, A-D-D-S is the way in my class I memorized it. Yes? So the globe preserves all of these. However, the reason that we want to do a map projection is so that we can take measurements quickly off of it. We can't really take measurements quickly off of the globe in terms of the distance. Now, computers are actually, this is a good point, computers are actually getting to the point where they can do all of that math fairly quickly. And I kind of alluded to that. That's what I was trying to get at when I said Google doesn't really care about the projection that it's showing, because when you click 2 points, you can actually do the math to calculate that distance along the surface of the globe and report that, which is what it oftentimes does. So, you know, who knows how long that will take, but in some ways, the map projection that the data is stored in nowadays matters less because of the ability of the computer software to calculate these values based off of the globe rather than using the coordinates that are actually stored in the points. But this stuff is still important because so much of our data for so long has been stored in these coordinate systems, and the areas and the distances that have been calculated is based on that measurement. So when we say that this is 3 feet long, or probably more likely this is 10 miles away from that point, we're talking about that all on the surface of the Earth. We're talking about that inside of a projection. All right, so we've got map projection characteristics. So one of the things that we showed on this thing here, we said shape, area, distance, or direction. These are the main trade-offs. However, the two principal characteristics are that a map can either be equal area or conformal. Those are the big, they can only be one or the other. They can be a mix of both. They can be like in between, not quite equal area, not quite conformal. It's a balance. But most map projections will report in the name of the map projection if they're equal area or if they're conformal. In other words, if they preserve area or if they preserve shape. Now, you can already tell this map of the United States of America is in a projection. And the reason that you can tell that is that the lines of latitude are curved. If the lines of latitude were straight, then it could still be in a projection, like the Mercator projection. Let's go back up here. The Mercator projection, all lines of latitude are still straight because the angles need to be preserved. Here in this one, the line is curved, indicating that angles aren't exactly what they. In other words, taking an angle measurement may be off. So this just shows equal area, direction, conformal. Like if you were to take measurements off a map, what that means. Conformal means that an angle here and an angle here should be the same if they're the same on the map. Obviously, they're not going to be because north, just think of it this way. North is this direction here, true north is that direction, and over here, true north is this direction. So north changes as we go across the map. What's true north? All right, so directions, this one would not be perfectly able to compensate for direction. So here's some examples using some older graphics. Okay? So here is unprojected, just showing latitude, longitude as Cartesian. So if you do have data that's not projected and you bring it up in ArcGIS, it looks like this. Okay? And that means that it's in a geographic coordinate system. And you can see the difference in that angle from a Lambert-Azimuthal projection versus a Cartesian latitude, longitude as Cartesian. Let's see. All right, here's another example. This distance actually may be, in fact it is, this azimuthal projection is very good because from the center of the map on an azimuthal projection, all lines are what we refer to as great circles. In other words, all lines from the center of the map are the shortest distance to that point. So in other words, the shortest distance from Anchorage to Seoul is if you follow this line. Okay? That's the shortest distance. However, that distance is, that distance, you'd actually be constantly changing your direction in real life because we're moving along this Earth, and we're actually turning more south because the map has arcs. Okay, here this is the true direction to Seoul. If I wanted to fly it, this is a Mercator projection. Remember I said all lines in the Mercator projection give you true compass bearings to that location. So this would be, if we wanted to just set our compass and go there, this would be the simplest way to do that. This would be the shortest distance way to follow that same path. So that shows two different reasons for those map projections. Okay. All right. So, what other things besides sailing a ship across the Atlantic do we need to have precise directions for? Well, cellular towers exist, but I think you've seen microwave towers. Microwave towers do actually have to be pointed at the next microwave tower in the system in order to communicate with each other. So pointing these directions matters. All right. Using different map projections will give you a different, it should make sense by now, that will give you a different distance if you're measuring the distance between 2 points. So the difference between these 2 points is 4,455 miles in a projection that was designed for South Carolina, which we shouldn't use in South America. Here, in the Lambert conformal conic projection, it's 3,150 miles between Buenos Aires and Caracas. Now, if you were actually compute that distance along the globe, it would be 3,193 miles. This is obviously a lot closer. Okay, we've already introduced, kind of like slipped it in, these ideas, but not really. You haven't. So when we talked about area, distance, direction, and shape, the way that we actually make a map projection that will have these properties is to use different shapes for our flat paper. So the reason that these are called map projections is actually because you could think of them like a flat surface that's been draped over the Earth, and a light source is used to, you guys are maybe a little bit young for overhead projectors, but maybe not. Got overhead projectors, put the thing on top of them, but we'll think of an overhead projector, put a translucent globe on it, and then you put a surface on it and it projects the information that's on the globe out onto the flat surface. That's really, mathematically, that's what's going on when we make a projection. So there are 3 different ways to orient that flat surface on the round globe. One is a plane, one is a dunce cap, like a cone, and then the final way is a cylinder to wrap the Earth, or to wrap it around like it's a toilet paper roll around the circle in the center. And with each of these, we can orient them a little off, but most standard projections either orient the plane or the cone or the cylinder on the equator, or they orient it on a line of longitude. Okay? And typically, a cone is only ever oriented north-south. So it could be a cone underneath the Earth or a cone on top of the Earth, but the cone is rarely placed anywhere else. Otherwise, it kind of makes the map look funny. I'll show you well, in fact, the map that I showed you earlier here. Oh, I went way back too far. This map is a conic projection, okay? And so you can imagine if you put the cone somewhere else, other lines would be going crooked, and it wouldn't look right. Okay? So it really only makes sense for the lines of latitude to be curved. And so a conic projection is usually either oriented along the top or the bottom of the Earth. And a cylindrical projection, though, can be oriented like this, which is actually the Mercator projection is oriented like that, or it can be oriented like this. Now, if it's oriented like this, it would look really weird. Can you imagine putting a light source in the middle of the Earth and projecting outward? Okay? So you project like anything that was on the edges would get really big, so the middle would look good, but everything on the sides would start to look huge. That's what happened in this one. That's what happened. So we put the center of the Earth right here, we put a light source in the center of the Earth, and it made the top and the bottom really big. That's the Mercator projection. If doing it that way, it would look really weird because like things in the east and things in the west would look big, and things in the middle would look all right. This gets used a lot, but only for mapping really small areas, right in the middle, right where it touches the Earth. We call the area that it touches the Earth, we call that the tangent. Okay, it's a mathematical term. So if we're using planes, or if we're using cones, or if we're using cylinders, those lines or points of tangency. So if it's a plane, it can be a tangent at one point, or it can be a tangent along a line, which actually forms a circle. Or if it's a cone, it can be tangent along 2 lines, which form 2 circles. Or it can be a tangent along 2 lines if it's a cylinder. In other words, it intersects the Earth at 2 points. That tube goes through the Earth at 2 points. So what happens is that the tangent, the areas where the surface, or the lines where the surface is tangent to the Earth, in those locations, the scale factor, in other words, the relationship between a true distance and the distance on the map, is close to 1 over 1. That's where it's 1 over 1. Anywhere as you get away from those points, the scale factor changes, and that's where the distortion occurs. As we get further away, in fact, or maybe this way, more and more distortion occurs. But the location of those tangent lines matters. So if we have this projection, and we lined it up right on Mississippi, we could create a map projection that was very precise just for Mississippi. And it might have 1 line of tangency if it just barely touched the globe, or it could have 2 lines of tangency. In fact, the map projection that the state of Mississippi has adopted as the statewide map projection is referred to as the Mississippi transverse Mercator map projection. This, it looks like this, where in fact there's only one line of tangency. It's lined up right over the center of the state, so that within the state there's very little error. And as you basically, if you use it to map somewhere well outside of the state, it's messed up. But inside the state, in fact, we can report how much error there is. We can report the maximum scale factor within the state. I forgot what that number is, but it's very low. I think it's actually a little bit above a meter, which is pretty low. Okay? That's the maximum error, or the maximum difference between the true scale and the map distance. All right, so that's line of tangency and scale factor, and those different types. So this is actually using a coordinate system or expressing a coordinate system. Here we've chosen the USA contiguous Albers equal area conic projection. It's a conic projection, it's an equal area projection, and you can see the various projection parameters that were chosen. We'll talk about these in a second. But the standard parallels are those lines of tangency. So this one has two places where it intersects. The standard parallels are the places where the cone intersects the surface of the Earth at 29.5 and 45.5. So it's 45.5 and 29.5. And so those are the areas where that reference surface intersects. And so as you get close to these areas, the scale factor is closest to 1/1. In other words, there's the least distortion in those areas. And there's a little more distortion in these areas, but depending on what you're doing, that may or may not be acceptable. If it's, if you're making a map of the whole United States, okay, being off by a few meters isn't that bad, especially if your map is just a map of which states voted for Trump and which states voted for Obama, or which counties even. But it looks good. It looks like you're looking down on the Earth using this map projection, which is a good look for a map. Okay, what do some of these other numbers mean? Well, the central meridian is just where, like when you pull the map up, where the center of the map is going to be. Okay, so that's this line, the central meridian. Okay, the latitude of origin is sorry, I actually messed up. The central meridian is this one, center of the map, east and west, and the latitude of origin is the north and south. Okay? Now that's going to be your 0, point. But what happens if you're trying to measure distances? The distances up here, the coordinates up in this quadrant, if this is my 0, are all going to be positive, right? But if I go here, they're all going to be negative, right? You learned that back in math class. So this is the origin, those are all negative, these are all positive, these are positive in the x but negative in the y, and these are negative in the, anyway, it doesn't really matter. What matters here is that oftentimes, I don't know, maybe geographers or geodesists didn't like to deal with negative numbers, but oftentimes these standard coordinate systems, what they do is they establish a false easting and a false northing. Here, this one didn't do that. Okay? But if they did establish a false easting and a false northing over here, a new 0, then all the numbers could be positive. And this is often done like so this map projection is not usually used for measuring distances. But like MSTM, that is used often for measuring distances. So it does have a false easting and a false northing, so that all the values within the state of Mississippi are positive. I guess it just makes things easier. So sometimes you'll see a false easting and a false northing. And then these are all the projection parameters that are required. And if we were to scroll down here, we would also have to establish which datum was used, and finally, we'd have to establish what units. So in order to establish a projected coordinate system, we need to establish what data is going to be used. We need to establish what units we're going to use. And then we need to establish if we're going to use a conic projection, a cylindrical projection, or a planar projection, and how that flat piece of paper is going to be tied to the Earth. Once we establish all that, we've established a map projection. Typically, you don't make up your own map projections. You can now, because you could just use this form, and you could modify, like if you wanted to center it a little bit further over into Illinois, you could. And there might be a reason for that. Let's say you were only going to make a map of this area. So you might want to recenter it so that it looks a little more centered on Illinois. But that's more of a cartography thing. We talked about that a little bit in the cartography class. For GIS, it's usually more important to be standard. In other words, to use a standard map projection so that when you combine your data with other people, there's a standard map projection that you can use to analyze your data so that it will overlay correctly. That's really what we want to learn in this class, is the use of standard map projections. So, these are some very standard, widely adopted map projections for analyzing GIS data and for storing GIS data in the United States. And actually, this one throughout the world. This one's referred to as the Universal Transverse Mercator, or UTM, coordinate system. So the UTM coordinate system is a transverse Mercator projection like this guy right here. All right. Now, maybe, probably not though, but maybe you're thinking in your head, if there already is this universal transverse Mercator system that works everywhere in the world, why did Mississippi make up its own transverse Mercator projection? And that's a good question. Let's look. I'm going to look at UTM zones. So here are the UTM zones. That's a small map. I want to make it bigger. We're going to get a bigger map. That's the same picture. Sorry. Images. There's a bigger map, maybe. That's still not that big, but hopefully. I think it might be big enough. Here, I'll zoom in. Whoop. Okay, so when I call the universe transverse Mercator a coordinate system, it's actually a set of coordinate systems. So everywhere in the world, you are in a UTM zone, but each UTM zone has its own projection. And that projection is lined up right in the middle. So its line of tangency is right in the middle of that UTM zone, and right in the middle of this UTM zone. So if you're mapping some area that's smaller than a UTM zone, then it's a very good standard map projection to use. Okay? If you're doing statewide information in South Carolina, where I did my graduate work, and so did Dr. Carr, South Carolina is entirely within Zone 17. I did my undergraduate work here in Utah, and Utah is entirely within UTM Zone 12. So the states are lucky, right? If you do it in California, though, statewide work, you can't use a UTM system because there's two different coordinate systems. If you wanted to use a UTM system, a transverse Mercator projection in California, it'd be best to establish one that ran right in the middle of the two. And that's essentially what Mississippi did as well, because we also fall right on the boundary between two coordinate systems, two UTM zones. We've got 15 and 16. We're right in the middle. So what Mississippi did was establish their own transverse Mercator coordinate system, and that's what's called MSTN. When we start the lab, I'll bring that up and show you that exists as a standard projection. So it's even ESRI said, okay, we'll put your special coordinate system in our software. So it gets used a lot for statewide. Okay, so that's the universal transverse Mercator system. Technically, it's divided into 60 zones. So there are 60 of which we saw that there were 7 or 8 in Mississippi. Now, even before UTM was established, many states established their own set of coordinate systems referred to as the state plane coordinate systems. And the state plane coordinate systems, for most states, well, actually, I shouldn't say for most states. For some states, there's only one, okay? Like Rhode Island, and I think even states as big as Tennessee only have one, but maybe I'm wrong. I had a slide on my other class, and there is a thing in your book that shows all of the state plane coordinate systems. But the Mississippi has 2, so that's the reason that it needs also statewide map projection. Somebody have questions? Sorry, I thought I saw it. Okay, that's the state plane coordinate system, and I said that. Mississippi Transverse Mercator System is our system. And what was interesting was MSTM was established back in the 90s. And when I first got here in the year 2003, MSTM was not yet in the GIS software. So one of the labs, we actually made it and created MSTM in the software because it's not that hard. It is a transverse Mercator system, and you could make it yourself. But it is in there now, so you don't have to do that. All right, so here's South Carolina showing up as all of these coordinate systems do have a false easting, not necessarily false northing, but they have a false easting. In other words, the 0, 0 is far enough south, so they don't need that, but the easting is necessary so that all the values are positive. And they're almost always in meters, unless you specify other words. By default, they'll be in meters. So they're very, very good for calculating areas and such. So here's UTM zones of the world. Technically, there are 60, but we say that there are 60, but technically there are 120, because there's one for all of the northern hemisphere, several one for the southern hemisphere. And the main difference is that the easting and the northing, false easting and northing is a different location, so that all the values will be positive. So for the state plane coordinate systems, they're all usually in the GIS software, and they have different projection parameters that are standard for their particular state. So typically, they'll use either Lambert conformal conic or a transverse Mercator projection. So oftentimes, states that are long and thin, these are the gray states, long and thin this way, we'll use a Lambert conformal conic, and states that are taller, we'll use a transverse Mercator projection. New York is like a difference here, but that's because they basically found 1, 2, I think 3 transverse Mercator projections there. All right, that's the last one. All right, so we ended about 10 minutes early. Anybody have any questions? Let's take a 15-minute break since we ended 10 minutes early. We'll come back at 2:45 and talk about the lab. So the lab is basically going to be you bringing GIS data in, changing the projection, and looking at the differences. And I'll talk about a few quirks about our GIS and projections. All right, so come back at 2:45.